Hello YouTube, today we're going to be doing another operator equation and we're going to find a more complicated operator equation for a more complicated circuit. It's pretty simple though, so we'll go right to it. So when the purpose of writing an operator equation is pretty much one way of going around differential equations by using algebraic equations instead of differential equations to approach the circuit. So to find V bottom denoted here, we can use a voltage divider, just like you normally would when solving for circuits, but instead of using, just like one component such as resistors, you can use impedance. And impedance is kind of like resistance. If you haven't watched the video, or if you don't know a lot on impedance or finding total impedance or what impedance is, I'd suggest you watch my total impedance video on my circuits playlist. So yeah. Okay, so you should know how to calculate impedance in the equation, so we'll get right to it and I'll do a quick gist of that. So for using a voltage divider, you simply take the component you want in the numerator, which we're going to define as Z2, over the sum of Z1 and Z2 times the voltage source. So that's the equation for using a voltage divider, very similar to when you learned it for the first time with more simpler circuits. But let's define what Z1 and Z2 are. I failed to do that for you. So let's do that. So the green there is Z1, and the blue here, the combination of the capacitor and the inductor, is going to be defined as Z2. Now, the Z represents impedance, and impedance for resistors, capacitors, inductors all have different definitions, so let's go over those real quick. The impedance of a resistor is its resistance, since impedance is like resistance. The impedance of an inductor is simply LP. P is an operator that kind of represents, that it does represent pretty much dt. So the derivative of impedance, the derivative of inductance, is the impedance for the inductor. And then we have the impedance for the capacitor, which is 1 over Cp, which pretty much says 1 over P is the integral of 1 over C. And that's pretty much what we got going on there for our definitions for impedance. And all you do is excuse me, to define what Z1 and Z2 are. So Z1 is just the Z R, which is just R. Now Z2 is a little complicated, so let's get to that. Z2 has a capacitor and a inductor in parallel. So you would solve for these impedances, treat them like resistances, and solve for resistors in parallel. And the resistors in parallel equation, one way to solve for it is using the product in the numerator over the sum in the denominator to get the equivalent impedance. So then we just substitute the definitions there for ZC and ZL, and we get 1 over P times LP over 1 over CP plus LP. Now we're going to go over here for a moment, and oops, I didn't, one moment. You didn't see anything. Just gave away a little bit of the work shown there. So if you were still following along, which I hope you are, you have the formula for finding the impedance in parallel. This equation is represented by this equation. So we showed that by definition, the impedance is represented by these variables here. So what we do is just simply use algebra to simplify this expression. So we're going to multiply by Cp over Cp. That'll cancel out the Cp in the numerator, and that will just give Lp. And then the denominator, we're going to have to multiply it by that quantity. So the 1 over Cp just becomes 1, and Lp becomes Lcp squared. And then we have the equation. Oh, whoa, sorry, we don't have it just yet. The key point in this method is to make sure that the coefficient in front of the p squared term is equal to 1. So what you do is you divide by LC. So they're divided by LC to the top and bottom. So the L's cancel in the numerator there, and you just get 1 over C times P. And then in the denominator, the LC goes to 1. You got P squared, and I just rearranged it by order of power. And then the 1 becomes 1 over LC because you divided every component there. So that is Z2. So we got that here. This is just Z2 is what we solved for. So now we're going to use the voltage divider. Now that we have every component that we need to use the voltage divider, we found Z2 and we have Z1. So let's show some work on that. Why don't we? So this is the equation for the voltage divider. And we're going to put in our V2, which we just calculated, and we have our Z1 is just R. And then our Z2 again, which is what we just calculated. It's the Z2 over the sum of Z1 and Z2. Then we're going to simplify by doing similar algebra as before. We're going to multiply the top and bottom by p squared plus 1 over LC to get rid of the fractions and then the numerator and denominator. And we got, let's see, p over c is in the numerator because the denominator cancels. And then we have to multiply r times p squared plus 1 over LC, which is that area, or that section in parentheses there, and then the denominator for the second component is canceled by our simplification here. So then let's rearrange that equation, times the s, and by dividing by r to make sure that the power of the p squared power is equal to 1, or excuse me, the coefficient in front of p squared is equal to 1, so we divide by r, and I'm going to rearrange the equation a little bit. So when we divide by r, we divide by r to the top and bottom, so we get 1 over rc, and I just put the p off to the side there, and then the p squared has the coefficient of 1, so that's good, and I just put the third term on the bottom down there as the second term, so we have 1 over rc times p plus 1 over lc when you divide by r. So that is the equation in variable form for the operator equation for the circuit times the s. So let's write that there in the summary page here. So we just calculated that, but look, we got to use these resistances and capacitance and impedance. We got to use those numbers. So we just plug in the values for R, L, and C, which were given in the original circuit. R was 0.4, C is 1, and L is 1, so the numbers are pretty easy. Well, 1 over RC is 1 over 0.4, 1 over 0.4 is 2.5, 2.5p. And the numerator and the denominator would be the same thing. Remember, L and C is just 1, so that means that last term there is just 1. And then we multiply by the s, and that is our operator equation, but actually using the numbers for each component there. And then, boom, we factor out the denominator there. Well, that should not be a p squared. We factor out the denominator just by using like quadratic formula, and you get first order variables for p, which is kind of what we want to make life easier in the future. So that's pretty much it. But going back to our summary page, here, we found the operator equation for the voltage, voltage bottom, for this circuit. That should also be, sorry about that mistake there, we already did the polynomial factoring. So there you have it. That is how you write the operator equation using a voltage divider for this circuit here. It's a little bit more advanced. It took a little longer than I thought, but I hope it helped in terms of separating things and figuring out what components you need to solve the overall equation. Hoped it helped, and happy studying.